So we should be good now. All right. It just took a little bit of time to figure it out, and I apologize for not getting it done any earlier. See if I can sign in here using that same password. It's not because of the wrong password that I couldn't access the Wi-Fi. It's something else. I don't know exactly what it is, but we'll figure it out. I'll figure it out. All right, so back to the class. And I'm gonna use this guy here. So what we'll do is same stuff we talked about on Monday, but this time it's going to be how we use the return value of one call as a parameter to another. Okay, so what we'll do is we'll start with a C program first. So we'll go to Notepad and start with a C program. Is this font okay, or is it too small? Okay, it's okay for people in the back? It's okay? It's doable? Okay. Because I can make it a little bit bigger if I need to. A little smaller? Too small? Is it too small right now? Okay, so that may be too big. We'll see. Is that okay? All right. Well, we'll type something first and we'll see whether it works or not. All right, so we'll do this int 8 underscore t. We'll call this subroutine 5, okay? Because that's all it's going to return. I think we might have seen this subroutine already, okay? And then we'll have another one, uint 8 underscore t. We'll call this 7, and guess what it's going to return? The constant of 7, okay? So these two are pretty easy subroutine to implement. And then we'll have the next one called sum, okay? So it is the sum of two numbers. The first one we'll just call that parameter A, and the second one we'll call it parameter B. There we go. And it's just going to return those two. It'll return the sum of parameter A and parameter B. So each one individually, well, we kind of know how to do these, okay? And then here's main. Here's main, and main has its own local variable. We'll just call it x here, and x is the result of sum, but what I'm going to pass to sum is going to be 5 and 7, or the result of calling those two subroutines. So this is going to be the first thing that we do today, is to kind of look into this and go like, how do we utilize values of to another routine? So the first question is, at any particular time, not counting main itself, what is the depth of subroutine call? Am I going to be calling like 2 or 3 subroutines, on the stack, or how many do you think we have on the stack at any particular time? So I will have you to think about that first. What is the maximum depth of subroutine? Okay, very good. It's correct because we call first. Okay, we push the result. Call 5, we put the result on the stack. Then call sum. So we wait for the return 5. Wait for the return of 5 before we call sum. So at any particular time, not counting main itself is not a subroutine. The depth of subroutine call is only 1. Okay, so this is kind of important because it really shows the priority of how to do things. Okay, so we'll go ahead and put this one on the side, and then we'll implement this in assembly. There we go. We'll go ahead and implement this in assembly. In assembly, it is important to implement main first, just because the program starts execution from the first instruction, from the first location. So we'll implement main first. Main is going to start with a decrement D. This is for allocating local variable x. And then the next thing it wants to do is to deal with the assignment statement. Okay, so we'll go ahead and implement all that stuff. It's going to have to call 7 first. So to call 7, we have LDI A, and then the dot 6 plus. Remember that stuff? Okay. And then we do a decrement D, STD A, and then the JMPI to the subroutine, which is 7 in this case. When it comes back to this point, then we will have the return value of 7 in register A. Well, register A is going to be messed up or overwritten by 5 and many other subroutines. So that means I can't really rely on register continuing to have the return value of 7 throughout this code. So that means, and on top of that, it is also supposed to argument 2 to sum. So I need to push it on the stack anyway. So might as well do it now. Okay, so now I decrement D and store to what D points to A. So we are pushing the result of calling 7, or the return value of 7. After that, what do? Well, we can now call 5. So kind of the same thing, LDI A, and then dot 6 plus, and then we have decrement D, and then we have STDA, and then we have JMPI to the subroutine. This time it's 5. By the time it comes back, we have to push that also on the stack. So we have a decrement D, STDA. So that this time we are pushing the return value of 5. So now we have both arguments of sum already pushed on the stack. So it's time to call sum. So that means we have a LDI A and then dot 6 plus again, decrement D, STDA, and then we have a JMPI this time to the sum subroutine. When the sum subroutine comes back, the first thing we need to do is to clean up the arguments. There are 2 arguments on the stack. Each one is taking up 1 byte. So we have to increment the stack pointer twice in order to clean up the arguments to sum. Now the stack is balanced. Then we have to store the return value of sum to local variable x. The return value is already in register A, so we got that. But how do we access local variable pointer? Local variable x. Okay. So in ST instruction to D with A is going to store the sum or the return value of sum to local variable x. Is that okay? So it might be helpful for you to kind of keep track of what the stack pointer is pointing to throughout the execution of this code, okay? Because the picture changes. So let's go back to the beginning, and I'm going to redocument, what the stack pointer is pointing to, okay? So the stack pointer is pointing to local variable x over here. But once I perform this step here, the stack pointer is now pointing to the return address of 7. When we get back before this decrement, the stack pointer is once again pointing to x, because the return address, even though it was pushed the call, it's the subroutine's responsibility to remove it from the stack or to deallocate. Kind of important, because you kind of have to look at the agreement between the caller and the callee, kind of figure out who is for what action on the stack. Do we have any questions at this point? That by the time we come back from the stack, no longer pointing to the return address, consume that particular byte in order to get. Okay. So after that, we push the return value. So that means D is now pointing to the return value of 7. And then at this point, we just push the return address again. So D is again pointing to the return address. But after that, on top of that, is the return value of 7. When it gets back here, D is no longer pointing to the return address. So it is now again pointing to the return value of 7. And then because we push this, so now D is pointing to the return value of 5. But if you want to see what is on the stack at this point, let's take a look. So what is on the stack at this point is at the highest location 255, is local variable x. Right below that is the return value of 7. And then right below that is the return value of 5. Okay? Is that okay so far? And this is where the stack pointer is pointing to, because it is the most recent push on the stack. Might want to do something like this. All of the instructions can potentially change the stack pointer, because that will help you get a better picture of what is going on when we call happens when the subroutine returns. So do we have any questions about this? This is all good so far? Okay, all right. All right, so main is pretty much done at this point. I have stored sum into X. So the next thing we need to do, if sum is an actual subroutine, is I have to clean up the local variable X now. Now, main is really not a subroutine, but I'm going to do exactly the same thing as if it is a real subroutine. And in this case, because main is supposed to return 0, now I know this is totally pointless, okay? But you can still say, LDI A with a 0, because A is supposed to be the return value, okay? It doesn't really do anything helpful here, because the very next thing we do is halt, okay? So that finishes main as if it is a subroutine. So now we just have to implement the other 3 subroutines. 5 is easy, okay, because all we do is to load the return value 5 into register A, and then we have to go back to the caller. So that's done by LD. You can use register B or C, either one would work. Okay, increment D, JMPB, and then 7 is kind of the same thing. The only difference is we are using LDI A7 instead here. So if you're really super lazy, you can actually do a JMPI to common return and put it here. Yeah, that's lazy. Is that okay so far? Okay, because the important part is we have to go through the sequence of these 3 instructions, the LDB instruction. Want the same 3 instructions all over the Let's jump to one that is already done and use that instead. So the question, am I saving and is it worth it? Okay, we'll count number of bytes first. EMP takes 2 bytes. Okay, the normal sequence instruction takes up only 3, because load is only 1 byte, increment 1 byte, the AMP is only 1 byte. So I'm not really saving a whole lot when it comes to the number of bytes. What about the expense of instruction or now I have 1, 2, 3, 4 instructions to execute instead of 3 instructions to execute. So I pay the price of 1 more instruction to execute to save only 1 byte. Not a very good trade, okay? That's not a very good trade. Yes.
Aren't most instructions 1 byte anyway?
Most instructions, except for anything that has an I, they're only 1 byte instructions with this toy architecture. Now, in case of actually running code in a modern architecture with caching, pipelining, and all the other stuff, is expensive because it breaks the normal flow of instructions. So that can potentially make caching not effective because you're not executing the program sequentially anymore. So the jump, especially if you jump to a very far location, invalidate, whatever it has cached is useless, okay? It can also potentially break a pipe also, because what pipelining does is it is executing a bunch of instructions in different all at the same time, okay? Do that. I think branching this is, but conditional branches, because the two depends on a subtract or compare instruction, which may not have executed yet by the time you start to decode instruction. So that means branching unnecessarily, generally speaking, is not good. So high price to pay.
You said that 2 bytes.
Yep.
So that's in 4 commands you have 5 bytes as
Yes.
opposed to 3 bytes in 3 commands.
Yes. It's not a very good trade. Yep. It's not a very good trade. So now, okay, so let's say we do not want to do this because it's not a good trade. Instead, we're gonna do this. Okay, copy and paste. Mm-hmm. Yep. And it can potentially be a problem too, because if I jump to the wrong label, then it's more messy. But if and paste, we the best way of doing things, because copying and pasting is not something that is that's a good thing. Um, 3 bytes have a construct fill out these 3 bytes like a macro. That will be perfect for this purpose. Okay, because it will just be using the same 3 instructions. You don't have the same 3 instructions. Okay. The other thing we can also consider doing, if you don't want to, if you want to minimize the amount of bytes used in the program, and also want to minimize the amount of time it takes to execute instructions, is to combine these 3 instructions into a single opcode. Okay? So we can find the microcode slices of these 3 into one opcode. So that is, with that approach. The processor is no longer a RISC processor. It is now starting to become a Cisc processor. Version to talk about what is Cisc versus what is RISC. Okay, we zoom back to this, later on. Okay, this is not a difficult program. What does RISC stand for? RISC. Okay, so we'll go ahead and check out RISC. And of course, the first link, tells you everything that you kind of need to know about it. It is called a reduced instruction set computer, which means it implements the fewest possible number of instructions to get a job done. Toy processor is kind of like that. Okay, it gives you very few instructions, and every with those very few instructions. Okay? And that's why it's kind of cumbersome. Okay, we have just seen a case where it is cumbersome. Okay, every time at the end of a subroutine you want to go back to the caller, you have to repeat these 3 instructions. That's kind of cumbersome. So what if we combine these 3 instructions into one single instruction, one single opcode? So that will save us space in the program. But because we also do not have to fetch 3 opcodes and only have to fetch 1, that will also help to save execution time. But that will lead us to the other architecture. It's called the Cisc architecture, CISC, which stands for Complex Instruction Set Computer. So the first letter is the only thing that differs. The other one is complex. That's the only difference. So traditional is a Cisc of the x86 descendants, like the i5 processor and all the predecessor of that thing, all of those are called Cisc processors. It has one single instruction called RET for return that will do the things that we do every single time. It has a single instruction called call, C-A-L, in order to wow. I mean, that's kind of cool because if you think about it, what that means is we can combine these 4 instructions and it just call 5. Okay? We can combine these 4 instructions, it's just call sum. We can combine these 3 instructions, it's RET for return. Okay? So the number of instructions, a number of available instructions is increased, but what each instruction can do is also increased. So why not? I mean, Cisc sounds like the way to go, doesn't it? Yep. So at the core level, the number of transistors at the level increases as a result of that. Your program not process. Okay, so now you have the rows. This turns out not to be the biggest constraint. They run out of one single resource first. Not power. You can put a right in the middle of the data center. It's something related to power. Okay. Physics. Yes, go ahead. Yes, cooling. Okay, so it turns out cooling is the biggest issue of data centers. Okay, now the first thing you have to remember is in physics, energy cannot be created or destroyed. Okay, change from one form to another form. In the case of a battery, change from chemical form into electrical form. And then from electrical form, usually it changes to either light or some kind of photon or photonic form. Heat is basically photonic as well. Okay, and for the most part, the energy of any computer, I would say 90 something percent of that. So you can only dissipate heat at a certain rate. Okay, so how many people have arranged or attended? You can be honest, okay? You don't have to raise your hand, okay? But you can be honest with yourselves, okay? So you can now imagine, okay? Imagine this scenario. So because we have a maximum thermal, they call it TP. I cannot remember the term, but it's basically the total heat dissipation of a processor. It can approach about 300 watts. Okay, if you have a super high-end like quad-core processor back in those days, and then your graphics card each is about 500 watts. Can be up to 500 watts, and then some people link two graphics cards, to kind of like so they can have maximum frame rate, when they play like realistic, first-person shooter games. So now you have 1,000 watts, okay, from the graphics card combined with the processor, we'll call it 1 kilowatts. And let's say you have, like 4 people, okay, or 5 people, okay. Let's say this is, in a game where you have 5 teammates, okay, that you guys have to be in the same room so you can scream at each other, okay. So you have 5 1,000 watt computers in the room, and the monitor is next to nothing compared to the power consumption of these computers. So what is the first thing that you would notice when you start this LAN party? No, the first thing is the jumper is going to break. The breaker is going to break because you're going to exceed how much current can go into a particular room or typical room. So a typical bedroom, with one circuit breaker, can have up to maybe 30 amps. Okay, that's pretty high for a single room as with a single 30 amp breaker. 30 amp times 110 volts is about 3 kilowatts. Okay, 3 kilowatts does not meet the requirement of 5 kilowatts. So the first thing that's going to happen is the breaker is going to break because you're consuming too much current. So you ask your parents and say, well, can we ask an electrician to install like a separate circuit or a bigger breaker, and just redo the wiring of that room. So your parent go like, well, that's going to cost us a lot of money, okay? But I got financial aid. Fine, okay. So we spend money, get an electrician, and then wire another breaker, into the room so you can have of kilowatts now, so you can barely deal with the kilowatt, and of all. You guys are all very happy. People brought in the computer, the monitor, not set up everything, and here goes the LAN party. Okay, the first half went really, and then the next half hour got a little warm. Of the winter, so nice. We just open the window, and then in the next hour, it becomes unbearable. Okay, nobody can survive in that room, even with the windows open, and it's only like 32 degrees Fahrenheit outside. Because what is 6,000 watts? Um, at full power, okay? And you guys use a hair dryer all the time. Well, I don't anymore, but it's never a problem. Because when you run a hair dryer, you run it for 10, maybe 15 minutes, right? And that's it. When you're trying to run these computers for an hour, not enough thermal mass in the room to absorb. So there's just no, to dissipate that. Turn on the air conditioner, it won't be able to get rid of all that heat from a single room. That becomes the biggest issue. Okay, so now how does that relate to the topic that we have at hand here? Cisc versus, why is it related? Well, the whole idea of RISC processors is each is very, it needs to know how to do. Okay, so each core is very small. But it needs to do more, it needs to execute more instructions to get the same thing done. But the bottom line is the number of processing or the amount of processing per watt is actually favorable when it's a RISC processor. So if you're not counting the number of clock cycles or how much time it execute to do one particular thing, and you're counting the number number of unit of energies like joules, okay, to get a particular computation done, RISC processors are actually better than Cisc processors. And that's why data centers are all using RISC type processors. They're using the same kind of processor that you have on your phone. This is also the reason why on your phone, they're not Intel, they're not x86 processors. Yep. One of the out there are others as well, but um, Arduino, architecture, but it's still 80 mega. The, but they're instruction. that's kind of interesting because we have to deal with this kind of stuff here because there are many processors out there that are RISC type. Okay? Now within the RISC family, it's also a spectrum. Okay, you have purist RISC processors on one end, and you have kind of hybrid RISC/Cisc processors on the other end. So a hybrid processor will basically look at things and go, it's worthwhile to implement a single return because it is so often. So it's worthwhile to increase the complexity of silicon just a little bit to save us a lot of time, trade-offs like that with the Cisc RISC, hybrid processors. So they implement certain instructions that could have been done in simpler instructions, but because of trade-off does favor having those have to be purists. On the other end, not entirely practical because things are boiled down to so any kind of code will take like this much code to write it. So the TTP, the toy processor here, is linked to the side. This because we have JMPI instructions that I could have J in the conditional branch instructions that has an I as okay. So that's kind of a little diversion from what we are talking about because I just felt this is kind of the right place to talk about it. All right, so we got 5, we got 7, and then we just need sum here. So with sum, it has 2 parameters, 2 arguments. So we can utilize the labels. Okay. So we can say return address is 0. Parameter A is return address plus 1, and then parameter B is parameter A plus 1. So all of these are basically specifying this offset from where the stack pointer points to these specific things at the entry point routine. Okay, so if it doesn't mean the value of the parameter. It's not even the address of the parameter. It is the offset from where the stack pointer points to the parameter. Okay, everything kind of to the stack pointer. All right, so with these things defined, we can now try to A first. Okay, so we'll get to parameter A, which is done by LDI. This is register C with offset A. This is actually okay, even though A is also the name of a register. It becomes the context. LDI instruction, the second item in the LDI instruction, always interpreted as an expression. So the assembler does not look at it's non-numerical as a label. So it's referring to label A in this case. And because that's just an offset, we have to add the stack pointer to C so that now C is the address of parameter A. But it's not parameter A that we want the value of the parameter. So we need an LD instruction to put it into a particular register. So now C is actually parameter A because of the dereference. And then we can do the same thing with the other one. So we'll do an LDI BB, which is really confusing because the first B refers to register B, the second B refers to label B. And that is strict, okay? First operand is always specifying a register, but the second operand specifies an expression that can be anything. So that's why the second refers to the label B. Okay. And then we do an add CD, BD this time, so that register B is now the address of, this is also kind of, okay, I'm going to make it a little bit more clear. Register B is now the address of parameter B. There we go. Is that better? Yep. For
LDICA.
yes,
After that, add
CD.
C, and also then it was the address of A. Isn't it the same case for the B?
This is label A, not the address.
No, I mean because C was referring to the address of A. Yeah?
Eventually, yes. So after this add instruction, then register C does contain the address of parameter A.
Okay. Then we are dereferencing.
Sorry again?
On the second line, on the line below that,
Mm-hmm.
we are dereferencing.
We are dereferencing, correct. There we go. Line numbers. Always helpful. All right. So we got to the address of parameter B, which is not what we want because we want to have the actual parameter itself. So now register B is parameter B, not the address of. We actually get to the value of that thing. Now to make things a little bit faster, well, I'm not going to change it. So that's fine. We'll do the addition here. So we're going to do an add B, C. Okay, it doesn't matter which way because both are temporary registers. So now B is actually param A plus param B. We have to copy that to A because A is technically the return value register. Okay. Now we are ready for the 3 instructions to end the subroutine. So we have the usual LDBD, increment D, and then a JMPB. So that's the return. Are we doing okay so far with this code? Yep. Mm-hmm.
I have a question about everything being relative to the create a lot of local variables, doesn't it become more of a hassle?
If you create a lot of local variables, now you have all the decrement Ds to allocate the space for the local variables. So so the stack pointer will be pointing to the very last local variable that you allocate. The return address is going to be like somewhere up there. Yep. So that is correct. This processor doesn't have enough registers. In the normal processor, register that is designated as what we call a frame pointer, or a frame pointer is one name. This the other. We'll just call frame pointer, but it's pointing in the stack. So that makes the calculation on the stack.
Does D represent because we pushed from B latest when we were before coming to the function C. So is it because that in line 56?
Okay, so what B is basically 2, right?
Yeah, exactly.
So we are basically saying, okay, what is the pointing to? Okay, it's pointing. We are calculating the address of parameter B based on the stack pointer. So are we doing okay so far with this code? Okay, so if it's okay, we'll, oops, Control A, Control C, and then we'll go ahead and try to assemble the program.
I think he used a semicolon on the 7 instead of
A semicolon? Okay, let's check that. Oh, okay, there you go. Thank you. Control A, Control C. And then the assembler should assemble a lot faster now. We'll check out how fast it's going to be this time. Shared. That's pretty fast. Okay, so we'll get rid of this one. It's not actually a part of this program, it's a leftover from the previous program. Go to RAM file and specify file download as, and we'll call this sum.csv. Okay, and then we can start up LogicSim. And because I'm using the wide format matching the monitor, we can actually now display more in the processor than before. We can even move some of this stuff over here. There you go. There we go. And then we'll also set it up to log a whole bunch of stuff. The program counter definitely needs to be logged. And then we'll log register A is important in this case because it is the return value. And then register D is also really important because that's our stack pointer. Okay. And then when we get back to RAM, we kind of have to think about how many locations we should be logging. So if you think about it, just kind of statically analyzing the program, this is how it goes. Location 255 is local variable X. Location 254 is kind of dual purpose. It's several purposes. The first thing it does is it is serving as the return address of 7, but when the caller is pushing the return value of 7 onto this same location. So it's kind of like dual purpose. And then we have the next location, kind of dual purpose as well. The first time it was used as the return address to 5, okay, from 5 back to main. But when 5 returned to main, this very same location is used to save the return value of 5, which is also serving as the first argument to sum. Okay, so at least dual purpose. And then the next one up is just going to be the return address from sum. So I think the entire program should only touch 4 locations on the stack. But we'll just be sure and log the 5th one also. And then we'll change the radix here. Oops. There we go. And I forgot to specify the log file. So we'll go to file and then specify temp sum.tsv as our log file. Close this. Control K to run it. Done. That's fast. I could not even see it, moving around. We used to be able to see the cursor, moving around. Is it done? Nope, it's not done because it was super slow. I forgot to change the click frequency. No wonder it looks that fast because it's not fast. Because the tick frequency is too low. It's at 1 Hertz. Okay, now we should do it a lot faster. Okay, Control K, zip, done. Okay. All right, so we're going to close LogicSim and then look at the log file. So go to Libreoffice Calc. And of course, it has to maximize itself. There we go. Okay, you still cannot see the bottom of it. Close. Okay. So we want to open up sum.tsv. We do the usual stuff. Okay, and then change the heading. This is our register A. This is the register D, which is also the stack pointer. And then we have the content of location 255, 254, 253, 252, and 251. Okay. So let's go ahead and minimize the width and then split the screen. All right. So let's check out the columns first. So we can see that the last column, or column H, was indeed not used. We can also confirm with the stack pointer that the lowest it got was FC. So that's why location 251 was never touched, because FC corresponds to 252 in decimal. So that's good to know. Did it actually compute the sum and store it into location 255? And the answer is no, it did not. So that we have a problem, because it never stored 7 plus 5, which is 12, back into X. So it returned the value correct, stored. Okay, never. I see. Okay, so the program did work. You can also see how certain locations are kind of like dual purposed. Like location 2 was dual purposed. Before it became 7, it was something else. It was first 09 in hexadecimal. When it was 09, it was actually the return address. So when we called 7, the return address 09 back to main. So that's 09 first, and then because the subroutine pushed the return value of 7 back to 7 here. You can also see how the stack pointer changed. The stack byte, and then main located that byte into 0. So the trace, by analyzing the trace, if you can open up the source on the side, how the stack is being utilized by each and every structure. So is it okay so far? Okay, cool. So your new assignment, there's one new assignment, for today. So I'll show you what it looks like, and then see if you guys have any questions about it. And this is our modules. Very good. Scroll almost all the way to the end now. It's recursive call. Okay. So first of all, do you think recursion, if I give you the C code to begin with, do you think it is difficult? It's more difficult to implement something that's recursive, something that is non-recursive. It makes no difference. Okay. The only potential downfall of a recursive subroutine, if it doesn't consume the entire stack and then start to overwrite the instructions themselves. So that could be bad. If you trace code, you can see that happening, okay? Because all you can see, that pointer keeps decreasing, and it starts to overlap with the code space, okay? So you can actually see it in the trace. So in this particular assignment or lab, however you want to call that, It has a few general questions to ask, things that you should know already by now. So I'm going to ignore all of that stuff. And this is really the beginning of the actual code that you have to implement. It's the Fibonacci sequence of numbers. And we're doing it the code way, okay? We're doing it the recursive way. So the definition of Fibonacci is if f is less than 2, it return whatever n is. So f of 0 is 0, f of 1 is 1, okay? But when n is at least 2, then you have to go for the else case. So now you have to go for the recursive of Fibonacci. So if then f of n is f of n minus 1 plus f of n minus 2. So that's basically the definition of the Fibonacci sequence. Nope. Any questions about the ternary operator? This is not the first time I used it. It's basically if then else, okay? If n is less than 2, then we evaluate 2, else we evaluate the last one, which is the recursive one. So when you implement it, you consider that as if it is. So the main function can be assumed to be something like this. You don't have to turn in your main function, although you do need it for testing your code, but you don't have to turn that in. And then the last question, or quote-unquote question, is not really a question, but the last one, gives you a chance to upload your source code, in assembly mnemonics. So this is where you upload it, and it has all. You have to observe, all of the agreements that we have talked about in this class. Register A returns the value. Register D is the stack pointer. Arguments are always pushed on the stack. Everything should remain balanced, and so on and so forth. So you have to write your code. Fibonacci, something that my as long as I agreements that we talked about, the code, no, you are writing the. Is that okay so far? Yes? Okay, so we are almost done today, despite, the little waste of time earlier today. We are actually pretty on topic. So now the biggest question is, you can see in the C code, we are calling f from inside f here. So the question is, does that change the way that we invoke a subroutine? The way we set up the return address, or the way that we deallocate arguments after it returns? Does not change a thing at all. Okay, so does this help to recursion? Maybe a little bit. I remembered when I took Pascal, okay, they talked about recursion, which was really cool. Okay, I kind of go like, but I did not really understand. Okay, what about local variable? There's only one variable. How can there be many copies of the variable? Time I get to language programming, I started to understand, like, oh, each invocation. So, okay, now understand it. So I'm hoping this has a similar effect to you. When you think about recursion, go like, oh, it's actually any different from calling a normal subroutine. It's just, hey, the label is the same. I'm here in the subroutine, but I'm going to the same subroutine. Is that okay? All right. I'm going to end this class right now. You guys can take a short break if you want. This assignment also you to finish, so you can, as long as it's done on that day. Okay. So you got plenty of time to work on this one too, but if you procrastinate, then you end up with a lot of stuff to do with very little time. That may not be advisable. Alrighty, cool.